Hello, everyone. A very warm welcome to the next or the current episode of Computer Vision Talks. Thank you for joining us on Saturday morning. Today we have with us Gaurav. Gaurav is a postdoctoral researcher at Mila. He holds a PhD in computer science from University of Waterloo. His research focuses on natural language processing and large language models. And today we are going to discuss his work, which was accepted at TMLR 2025. It's called Lit LLMs. So I think it's super relevant to the research community, given that related work section is what we struggle with the most. So over to you, Gaurav.
Sure. Okay. Thanks for the introduction. So, hi guys, my name is Gaurav, and I don't think I can add much to what Shambhavi already said. Yeah, I'm a postdoc at Mila, and I work on LLMs, NLP. More specifically, I'm looking at how we can use LLMs to accelerate science, and this effort is towards that direction. So, if we are okay, I can start the talk.
Sure, sure. Yeah.
Okay, so today we'll do a deep dive of this paper called Lit LLMs, LLMs for Literature Review. Are we there yet? So this work got accepted at TMLR 2025 recently. And in this work, we are tackling the challenge of writing literature reviews because as researchers, we know how time consuming writing lit reviews can be, and it takes a lot of effort. And especially these days, for machine learning, there's like thousands of papers popping up every day, so it's very difficult to keep up with the trends. So yeah, and I myself have countless times stared down the a blank draft of literature review because it writing literature review doesn't just mean you write something. You also have to first go through a bunch of papers, familiarize yourself with what's going on, and then you have to make a plan, and you have to then finally write. So there's a lot of things that go into writing literature review before you actually write the review. And in this work, we are trying to explore the zero-shot capabilities of LLMs to assist with the process of writing literature reviews. And before we move forward, I would like to clarify here that in this work, we are not trying to like automate the entire process of writing literature reviews. So you just click a button and then you it does everything for you end to end. Because besides taking out all the fun from the process, we wouldn't know how to judge the quality of the generated reviews. And more importantly, the purpose of writing literature reviews is not just to write a literature review. The purpose is for the researcher to know what's going on in their field so that they can situate their work better in that field. And in the meantime, like learn about a lot of other things that people are doing, right? So in this work, we break down the task of writing literature reviews into two. So first, we retrieve relevant works given your research idea. And after we have those related works, relevant works retrieved, we move on to the step of generating a literature review. So here's our overall approach, and it all starts with the research idea that a researcher has. So they input their idea to the system, and then we combine keyword-based and embedding-based search to retrieve relevant papers from a large database of academic papers. And once we have those relevant papers, we re-rank them according to users' interest and some other criteria that I'll go through. And once we have those papers re-ranked, um, we then pass it through the generation step where we feed where we feed an LLM those retrieved re-ranked papers along with some other plan that the researcher has, and then at the end we generate the review. So let's discuss what exactly is going on in this retrieval module. So once you input your research idea, it's broken down into keywords. So let's say you enter a big abstract. So that big abstract is broken down into multiple keyword queries, and we pass them through a keyword-based search engine, and we get some papers from there. Simultaneously, we are also doing embedding based search. So we take the embedding of your abstract, and then we pass it through a bunch, like a really large database of academic papers, and then we compare the cosine similarity of papers in the database versus your current paper, and then we take the ones which are the closest, top K, and we combine them, and then we use an LLM to re-rank these things. Uh, uh, so for keyword-based search, we are using Semantic Scholar and SERP. I mean, that's what we used in the paper, but you can use some other academic database like OpenAlex as well, because it's free, has a lot of requests you can make in a day, and so on. So, and if you don't know what SERP is, it's essentially an API to do Google search without, them blocking you for being a bot. And for the embedding based search, we use the Spectre 2 database. So we use this database because it is a collection of 150 million abstracts from scientific articles. And okay, just let me talk a bit about how we like use this Spectre 2 database in our task. So 150 million documents is a lot, right? So we need to first index them, and this database comes. So this data base comes with like these 908 compressed files, and what we do is we use Paste to index them all. So for every query document that we have, we essentially do this process of, getting the embedding of the query, and we already have the embeddings of these 150 million documents. And for each
Gaurav,
of
this.
those,
Yeah. So are you indexing the embeddings or are you indexing the documents? And what is the metadata you're using with these embeddings?
so we're indexing the embeddings here. So this uh, database comes with like the embeddings themselves. And those embeddings are called Spectre embeddings because, the database is called Spectre. So we have 150 million embeddings, and we are indexing that.
I see. Okay.
So yeah, for every query, we do this indexing. So it's essentially like pre-computing your search results, because in this case, we know what are like our query sizes, a query set is fixed, right? So we are pre-computing so that when we do this or like on at runtime, it's faster because you cannot do a search through 150 million documents on the fly. So anyways, yeah, we index them all, and then we extract, like we save the top K results for each query, and that's what we have in the end. And moving on to the re-ranking step. So this one. So here we have a couple of approaches. One is to use the cosine similarity of Spectre embeddings itself. So this is different from like this task, right? So here you have combined documents from like both the keyword based search and the embedding based search. And then again, we are like essentially doing this Spectre embedding thing. We are computing the embeddings of the documents that were retrieved by the keyword based search. And then we are including that in the mix as well when we are like doing the C ranking. So we aggregate the results of both these searches, and then we do like one final embedding based sort, and we choose top K from that. So that's one approach we use for re-ranking. The other one is LLM-based re-ranking, and one naive way, like one, well, I wouldn't call it naive, but it's, I guess, one of the first methods that were proposed. So it's called permutation re-ranking, and it's very simple. You just pass in an abstract of your research idea and then the abstract of your top K documents, and then you ask the or prompt the LLM to generate a ranking like this. So let's say you have three documents retrieved for the sake of this example. The output of the LLM in this case would look something like this. So given the query and given the query abstract and the abstract of all these other retrieved documents, the output is literally the final ranking. So we don't do any other sorting on top of this. So this is one approach. And then this is what we propose. So we use debate ranking with attribution. So what's cool about this method is the input is the same. You pass in the query abstract, you pass in the abstract of all the retrieved papers, and then you ask the language model to first generate arguments that would that would be for relevance of this like of a given candidate, and then you also ask it to generate arguments against uh, the inclusion of a particular candidate paper in the literature review. And these arguments, we ask the LLM to situate its arguments with respect to other abstracts as well, because we are passing them like all together, right? So it has a chance to compare the abstract of a like current candidate paper with the abstract of other candidate papers in the retrieved set of results. And what I mean by attribution is all of its arguments are backed by evidences that it extracts literally from the um, abstracts of like respective papers. So it's not hallucinating things. We have evidence of all its arguments in there. So once we have generated these arguments, we then ask it to provide a final score. We call it relevance score. And this score is supposed to be proportional to the probability of a given candidate paper being included in the literature review. So, so far, any questions?
I think we are good. We're good.
Okay, yeah. So this is our proposed method. We use debate ranking with attribution for like as one of the like experimental settings. And then moving on to the generation module. This is pretty straightforward. So there's not a lot of fancy things going on. You have your query paper abstract, you have your reference papers abstracts, then you pass them to this LLM, your favorite LLM, along with a plan, and then you generate related work based on this input. So let's move on to the evaluation and findings in this paper. So we use this multi-X science data set for our experiments, which is a data set where the task is to generate the literature review of a given work, given the abstract and a list of references that it has. And then this is a data set that we construct ourselves, or rather, it's a protocol that we use in this work to avoid test set contamination during the zero-shot evaluation of these LLMs, because it's possible that some of the papers that we are trying to generate the related work for, the LLM actually knows about that paper, so it might be easy for it to game the system. So that's why we propose this rolling eval, which is essentially you take the you t- you your test set is essentially a set of the most recent papers from archive, which are strictly like after the cutoff date, knowledge cutoff date of these LLMs. So these language models would not have had a chance to, look at those and then cheat their way out of this. Make sense? As for the metrics, for retrieval step, we use these three metrics: normalized recall, precision, and coverage. Precision, I think everybody knows what precision is. And in this work, we define coverage as the number of papers in top K uh, that were in the like ground truth as well. So let's say we are testing for a given abstract, we have a truth list of references for that work, right? So coverage means how many of the uh, how many of the results in the top K were actually present in the original work, original list of references as well. So that's what coverage is. And then normalized recall is slightly um, funky thing. So I'll get into the details of what normalized recall exactly is in one of the later slides, but this is the formulation. So in vanilla recall, you would normalize this whole thing by the number of ground truth samples that you have. Instead, what we do is we first take an intersection of the number, like we first take an intersection of how many documents in the retrieved set were actually present in the ground truth list of references as well. So we use this metric to evaluate the ranking quality of a given approach. And next up, for the generation step, we have these metrics for evaluation. So Rouge 1, Rouge 2, Rouge L, these are very standard metrics for summarization task, where you compare two pieces of text. Then BERT score is it's an embedding based scoring system where it's like you can think of it as cosine similarity, but using BERT score, using BERT. And then we have Llama 3 eval, which is an open source alternative to geval, which was proposed in prior works. And what geval is it's a LLM-based metric where you compare two free-form texts on a given criterion. And what's cool about this method is you first give your like reference text, and then you give text that you want to compare, and then you ask the LLM to generate a rating on a certain scale. And instead of taking that hard output that the model like generates, let's say it generated that okay, it should be rated 4 out of 5. So instead of taking that 4, you take look at the distribution, like what's the probability of the other scores being generated at that time step, and you take a weighted sum of the those like probabilities and then those like actual scores. So let's say your rating scale was from 1 to 5. So instead of just looking at the score that the model generated, you would do the probability of score 1 being generated times 1, then probability of 2 times 2, and so on. So this gives us a soft distribution and helps us better model the underlying distribution of the LLM. And finally, we do human evaluation to see if our method even works or not. So I can move on to some quantitative results now, unless there's any confusion.
No,
Okay,
all good. Mm.
so in this table, we show what the coverage was for all these different methods that I just talked about. So here, single query means that in that initial step of converting an abstract to like keywords, we only construct like one keyword based search query. Whereas multiple queries would mean that given an abstract, like from a single abstract, we construct multiple like short search queries that we then feed onto these like search engines. And if you look closely, the coverage is not super high. So in best case scenarios, it's like almost like 10%. So it's not recovering almost 90% of the papers that were retrieved in the that were actually cited in the original works. And this is a very difficult problem to solve because humans write literature, like everybody writes literature reviews in different ways, right? So how do you determine um like how do you model the way people cite, because there's also a lot of disagreement between individual humans, right? So if I write something, I'll maybe include some papers. If you write something, you'll maybe include some other papers. There might be an overlap, but who knows how big that overlap or how small that overlap is going to be. So overall in this table we see that like constructing multiple queries for a given abstract and then combining it with the Spectre database gives us the best results so far, uh, which I guess makes sense because Spectre 2 has access to 150 million documents. And then we are here constructing multiple queries for a given abstract, which potentially diversifies the pool of retrieved candidates. Okay, let's move on to the other set of results. So this curve shows the normalized recall curve for different retrieval settings. So I'll quickly go over what like the thing before the comma is and what thing after the comma is. So the first part in this legend is the thing we use for search engine as the search engine, and the second part denotes what's the ranking model that we use. So we start with just a simple semantic scholar search here. So you give an abstract, construct keywords, and then you pass those keywords to semantic scholar. You don't do any re-ranking, and this is our baseline. And in this curve, um, this final point, so okay, let me actually talk about this curve as well. So uh, since we do top 100, so that's why the scale on x-axis is like from 1 to 100. So once we do this semantic scholar search, we take the top 100 results as our candidate list. So what this final point at k is equal to 100 means is the potential of a particular search engine in achieving, like, what's the maximum that a search engine can achieve. So we start with a simple semantic scholar search without any re-ranking. Adding this permutation re-ranking helps slightly, but it doesn't really make a lot of difference. But when we replace this GPT for like permutation re-ranking with debate re-ranking, we see a lot of gap here. So for instance, it's at k is equal to 25, it's more than 10% difference here in normalized recall. And when we replace the debate re-ranking with a Spectre re-ranking module, we see that the curve further improves. And let me talk about what like improvement in this curve essentially means. This is just bringing back. So when I say that this green curve is better than pink curve, what it means that this re-ranking module has a better sense. It's better aligned with what with how humans cite some things, and it has put in those relevant works ahead in its top K as opposed to pushing them to the very end. So let's say in this example we in this re-ranking step, it generated this ranking of 5 documents, and we know that out of these 5, 2 were actually present in the ground truth. A bad re-ranking module, I mean a worse re-ranking module, I wouldn't say bad, a worse re-ranking module will put in these documents that were in the ground truth towards the end, and a slightly better model would put them like ahead of it, and an even better or the best out of these will put all these documents that were in the ground truth towards the very top. So you wouldn't have to sift through a long list of documents before finding that okay, this document is really relevant. So that's what we mean by ranking quality here. And if we go back to this curve, a higher value at a lower K denotes like that particular method achieves its maximum potential very early on. So let's say the maximum normalized recall that we could get by using a semantic scholar search is this is 65 or 66%, then it would so if we use this Spectre-based re-ranking, it would mean that towards the top of its like search results, we'll find more papers that were included in the ground truth compared to like these other baselines, where all these papers in the ground truth, they were pushed towards the very end. And then these two curves, we add in Spectre database search. So Spectre database search as well, like that embedding based search as well. So this orange or brown curve represents that we did that embedding based Spectre embedding based search for those keywords. And we immediately see that the potential, like the final maximum potential, is way higher than just using keyword search. And when we combine both Spectre and Semantic Scholar, we see that there's like a slight improvement there. This might be because there's already a lot of overlap between what Semantic Scholar gives us and what Spectre retrieves, because Semantic Scholar also under the hood uses some sort of Spectre embedding based ranking. So there might be some overlap. That's why this gap is not as big as this one. Um, okay, and what else? Okay, yeah. So overall, we see that combining keyword-based semantic scholar search and embedding-based Spectre search with like with debate ranking, Debate re-ranking gives us the best normalized recall curve out of them all. And by best, I mean at a lower value of k, like you'll see more relevant results in towards the top as compared to towards the end. So there's even, so if we look at this k is equal to 25 again, it boosts from less than 30% to almost 60%. So there's like a 2x jump here, which goes on to show that the quality of ranking generated by debate re-ranking is like much better. Okay, I know that was a lot to take in. So if you have any questions, I can take them on, or I can move forward.
I do have some questions of me on metrics in general, but I think for me it would be better to ask them towards the end altogether. But if anyone from the audience has a question, please feel free to drop them in the chat or ask to unmute you so that you can have a discussion. Mm, okay, I think I'll
Look,
interrupt you.
okay, looks like we're good to go. So we observe similar trends for precision as well. So as you can see, it's almost double the precision of the baseline model. And yeah, it just goes on to show that like debate re-ranking really works, or asking these models to argue, like generate these arguments, it really works. And here are some results for the generation setup as well. So in here, we evaluate it on, so these results are on one of the rolling eval data sets. This was constructed for the month of August. So what we did was we took in archive papers for August. We shortlisted 500 out of them based on, how good they are. And then we used them as our test set. So so we have these root scores, which are like typical summarization metrics where we compare the uh, generated reviews by the LLM with the actual related work section of these works in these works. And then we have this BERT score metric, which is like a similarity metric. And then we have Llama 3 eval listed here. So what we can observe right off the bat is well, we see that these plan-based models outperform their non-plan-based counterparts. So if you see, all the plan-based models have better root scores. And one other thing to notice here is, okay, one other thing to notice here is that when we look at BERT score, well, on paper, I guess it has a similar trend to root score. We don't see a lot of sensitivity here, so it's like that teacher who gives everybody good marks, so no one knows what's good and what's bad, sort of like that. And something like that is also in the root scores. So like these scores are like super low, and it's very tough to you know make sense of these super low scores. Like, do they really reflect the quality of the summary or not? Because these are just like n-gram based approaches, right? So they don't look into the semantic meaning of the generated text. So that's why we opted to use something like this, Llama 3 eval. And okay, why didn't we use GPT here like everybody else? Well, A, it's expensive, and B, we don't, this evaluation metric is gonna change if we use GPT, right? So because their endpoints keep changing, so you don't know what exactly is going on behind the scenes. But if you use an open source model like Llama 3, in this case we use Llama 3.170 billion. So in this case you have very precise control over what your evaluator is, and there's not a lot of stochasticity introduced there. So these results are very reliable. And moreover, we also did an experiment in the paper where we show that Llama 3 eval is, the trends shown by Llama were very consistent, highly consistent with the trends shown by GPT. So there was like just a few point difference, but the overall trend was the same. And one other thing that I noticed here was the gap was also slightly like more tangible compared to like these other metrics that we see here. So like, how do you discern between a text which has a root 2 score of 5 and a root 2 score of 7? So it's like slightly less tangible compared to one metric that says, okay, this is 60, this review gets a score of 66, this one gets a score of 75. So you have some sense of, okay, this one is better. And these are results on the multi-X science dataset. So in here, so it's the same sort of experimentation regime, but on a different data set, and we have like more baselines compared here. So these are some other, these are some extractive summarization baselines, some abstractive ones, some zero shot models, some open source zero shot models, and overall the story is the same. Like the plan-based models, they outperform the non-plan-based models by quite a bit. And the best model out of them all in our case was GPT-4, but Llama 3 was also not that far behind. In fact, on Rouge 2 and Rouge L, it's very consistently close. Moving on to the human evaluation in our case. So in human evaluation, what we did was we showed these experts uh, two reviews, one generated by a zero-shot model and one generated by its plan-based counterparts. And we do this for Llama 2 and GPT-4. And then we ask them two questions. We ask them to first rank the reviews that they like. So if they like one review better, then they rank it one, the other one it then goes to rank two. And then we also ask them to identify instances of hallucinations in the generated reviews. So overall in the human study, what we found was so uh, the human evaluators preferred plan-based reviews over like non-plan-based reviews, as we can see by these counts. So out of all the instances, there's like 30 plus instances where they liked the plan-based output of Llama 2 compared to close to, I guess, 18 um, instances where they like Llama 2. And then the next, I guess, this one is more important for me, or it was, yeah, more impressive to me. So we see that the hallucination rate when using a plan-based model got reduced by quite a bit. So it's like more than 50% here, or it's close to 60% actually. And this one for Llama 2, it got reduced to about 40%. So that was one of the like nice things about this plan-based approach. Like providing this fine-grained control can help the model avoid hallucinating facts. So that's it for our experiments. I can like start gathering what I just talked about in the past few minutes. So in this work, we proposed a novel pipeline that decomposed the task of literature review into LLM-assisted retrieval and plan-based generation. And the two-step LLM-based retrieval strategy combines keyword-based and embedding-based search, and it's further enhanced by re-ranking with attribution that improves the relevance of the retrieved results. Then we have the plan-based generation approach that significantly reduces hallucinations and offers the researcher at the end more control over how they want to, write, how they want the review to come out at the end of this whole process. And then we also proposed this new rolling evaluation protocol to avoid test set contamination when we are evaluating these zero-shot models. So to answer the question in the title, are we there yet? Can we completely rely on these LLMs to write our literature reviews for us? So the short answer in this case is not quite, but we are getting close. So we started this work like more than a year ago, and if you are keeping up with the trend in the past few weeks or months, this whole LLM for research thing has just exploded with systems like Deep Research, AI Co-Scientist, Scholar QA, PASA, you name it. There's like a lot of agents out there that are trying to do something similar. But what they're trying to do is like they're trying to automate the whole process of writing literature review. So you enter your query, and then you end up with like a really long text and then a bunch of facts being thrown at you at once. So instead of like making your lives easier, it's it in some sense the cognitive load is increased. So which is not what we want. So in this work, we opted for an approach that puts the researcher in the driver's seat, and they have the full control over what they want in their literature review and how they want to write the literature review. So here's a link to the paper, and we'll also release this tool um, soon. And I guess we have some time, so I can show you a demo of how Little LLM works. So this is our current system. So let's say you have this input idea of, let's say you want to explore if LLMs can rediscover scientific concepts based on basic building blocks. So you just enter your abstract, and to save some time, I've already entered it. And then you click search, and then you'll see a bunch of papers being retrieved from the web. For now, we're not showing a lot of papers. It's like a demo state, but this can eventually be increased. And once you hit enter, you'll get some search results, and for each document you'll see why this should be included, why they shouldn't be included, along with the relevance score. And then you can like select your papers that you want to write your literature review on. They're all gonna appear on this side. And either you can generate a review directly. So you just, in this case, what's happening is we are passing the abstract of all these papers and then prompting it to generate a review. Or a better way to do this would be to first ask the LLM. So this is a summary, sorry, this is a review based on just the abstracts of these papers. And what we also can do here is we first ask the LLM to generate a plan for the review. So it's going to identify certain themes, and these themes are editable. And so you can see in the plan like what papers it plans to include for this theme and what this theme overall is going to be about. And if you like the theme, good. If you don't like the theme, you can edit it, and then you can uh, tweak this review to follow this plan. And if you give it a few seconds, okay, yeah. So the new review that it generated, it has organized it into these different themes. And if you want like more fine-grained control, you can even use this option where you say, okay, this review should be 10 sentences long, 20 sentences long, cite this paper on this set on in this sentence, cite that paper in that sentence, and so on. And then this review can be further fine-tuned um, based on this sentence level plan. So that is Lit LLM, folks. And I'd be happy to discuss more about it. If you have any questions, we can take them now.
Yeah, that was a great presentation, and thanks for the demo as well. It looks pretty cool, aesthetically pleasing. Are you planning to release it soon?
Yeah, so we are planning to release it pretty soon. We're just conducting some internal testing to make sure that it's not going to break when other people try to use it. And I'm also adding some other features into it. So based on like some few initial rounds of testing, we got some feedback like what features people want in this tool. So one feature is if your paper doesn't appear in the search results, you can directly add the paper to this set. And the other one I got was yeah, like improve. So instead of saying 1, 2, 3, 4 in the review, maybe it would make sense to give them like a list of references so that the user knows, what one means and which paper does two mean, refer to.
Mhm.
The other one
Mhm.
was ability to export citations. So there are some like small updates that we are working on. And yeah, once it's like stable enough, we'll release this to the public.
Also, I have some general questions. Sure, there are some comments for you, thanking you for the talk, Gaurav. Um, I'll continue with my questions. So, one thing that comes to my mind is that something super similar can also be very useful in niche research areas like legal or clinical medicine. So, do you see a use case where you might need to fine tune the LLM, or since in this use case it works without it, right? So, do you think it's scalable?
Oh yeah, of course. So right now, I'm focusing specifically on academic search engines. So in this case, we are using Semantic Scholar, OpenAlex, and a Google search. So we are combining results from all of them, and it's not a lot right now, but this can be easily increased. This is just for demos. I've kept it like lower, but for let's say for legal cases, you can just switch the database to something that deals with legal documents, and then it's gonna work like out of the box. I think even Google Scholar has a version for legal documents, right? If I'm not wrong.
It has a
So
patent version. Yeah. Yeah.
yeah.
Mm. Also, there are quite a few questions in the chat from Basma. So she asks, what were the main motivation behind this work? What were the challenges you faced? And if it is a RAG-based approach?
So the motivation was to make our lives easier because I can't remember how many times I've like started with this literature review, and then it's just very difficult to keep up with the current trends. And yeah, and every other day there's this new paper that pops up. So how do I decide which ones are worth my time? So a system that tells me that is going to be super helpful. So that was the initial motivation. The challenges we faced were, I guess, outlined before. So one, the overall coverage rate is quite low. For instance, it's just 10% right now, but we are working on that step to improve it, and there are some ways to improve it that we are looking into. The other challenge was how do we reduce hallucinations? So we noticed that using attribution for re-ranking during the re-ranking step, it like really helped. And there was also one small step that I did not mention. So when the LLM generates these evidences, right? So how do we know that these sentences themselves are not hallucinated? So there was this small verification step that we added, and that further, I guess, improved. So these are some of the, like, I think these would be the two topmost challenges that we faced in this work: reducing hallucinations, and then second one was, yeah, retrieving more relevant papers. And the last one was, is this a RAG-based approach? Yes.
Thanks for your answers. Given the second answer, you talk about hallucinations. So, apart from tracking hallucination or factual errors, which additional quality metric do you think would be important for such kind of literature reviews? Example that came into my mind was thematic coverages or source diversity.
Yeah, evaluating these reviews is also very tricky. Like, how do you come up with these metrics? Because everybody might have a different sense of what a literature review looks like, right? So, yeah, so that's why we rely mostly on human evaluation to study the to measure the quality of these reviews. And I think out of all these like automated metrics, I would say an LLM-based metric like Llama Eval would be the best out of them all, because it not only takes the order of sentences, but it actually knows what, it can process the information or semantic information in the generated review. And actually, most importantly, this is a reference-free metric. So if you have a reference text to compare with, good. But if you don't have it, you can provide some metrics or rubrics of your own, and then it still works.
Mm. Okay, great. Another question. For the audience, please feel free to drop your questions in the chat. We are reaching towards the end of the talk. So I might run out of my questions. And if you have any, it would be nice to continue on. So I have one major one, which was like um, around citation quality and transparency. So there might be some shallow citations, so the paper might not be very relevant or it's very tangentially relevant, but it still gets included. So are there ways to give user more transparency or confidence in each citation's significance?
Yeah, so that's what we are trying to achieve with this relevance score here. And while this is not perfect, uh, at the end of the day, we rely on the researcher's ability to determine whether or not, a certain idea is shallow or it's actually worth including. Because sometimes, even in my case, when I look at some papers, the title sounds very similar, the abstract sounds very similar, but it's not exactly what I want to be working on. So these are some nuanced decisions that a researcher can make to like enhance the citation quality.
And one more thing that I was wondering was that you combine multiple ways to analyze a given input. For example, you have an embedding based ranking and you have an LLM based ranking. If you take just the LLM based ranking, what were the drawbacks? Like, what was the motivation behind adding embedding based ranking as well?
So, okay. So the embedding based model that we used, that was trained on millions of scientific articles. So these vector embeddings. So I already mentioned that vector embeddings has like 150 million documents, and the sorry, Spectre dataset has 150 million documents, and these vector embeddings were trained on a few million of these scientific articles. So the motivation behind using these embedding based models is that once you train this on your data set from your domain, they're very fast to run at like runtime. So in fact, like right now, there's no like in this demo, sorry, in this demo, there's no embedding based re-ranking right now, but you can add it here, and it's gonna be like super quick. So compared to like an LLM based re-ranking approach, which might be slightly slow depending on how many documents you're asking it to compare at once. Yeah, so I guess short answer would be an embedding based approach is more scalable compared to an LLM based re-ranking approach.
Makes sense. Okay, great. Yeah, so these were some questions from my end, and I seem these are all. I don't see more questions in the chat. So yeah, thank you so much, Gaurav. One last thing I would like to ask is like scaling up to future. While you were presenting the talk, there seem to be so many use cases. Like usually, a research paper is a team effort, right? So Lit LLM being a collaborative platform where you have some saved searches from the whole team or annotated references that multiple co-authors can share or use simultaneously. I can see so many nice use cases. So yeah, your work definitely has given some foundation to this whole scope going crazy wide. Thank you so much. Okay, there are some questions as we go. Oh, there are more questions. Okay, sorry. Yeah, let's go back to answering the questions. Uh, Kunal is asking, can you please elaborate the recall normalized stuff? And how many human evaluators did you try with?
Okay, yeah, I guess yeah, those are two great questions. Um, so the best, okay, so this is the formulation that we use for normalized recall, and how it works is we can let's work through an example. Let's say you have let's say a given query paper cites 50 reference papers, and then we are retrieving from these search engines we get, let's say, 100 like papers, right? So retrieved intersection ground, and we know that for the sake of this example, let's say there are 10 papers that were retrieved by the search engine that were also cited by the original paper. So in that case, this retrieved intersection ground truth would be 10. And then what we are trying to measure here is if we break this down, this recall metric along this axis of K, how early are we seeing those papers in this set? So the best case scenario would be those 10 papers would be like really up top. Let's say, so they'll all appear at the very beginning of the search result. So in which case the graph is going to look something like it's just going to shoot up to 1 at k is equal to 10, and then it's going to flatline there. So that would be the best case scenario in this case. Uh, but of course that's an ideal case, but it doesn't happen actually. So That's what we are trying to measure here. Like how early do these relevant search results appear in its like right in the top K. And the other question was, I guess, how many human evaluators? I don't remember the top of my head, but I think you can find it in the paper. I think it was, I don't want to quote a wrong number, but I'll have to double check that. Mm, is there another question while I find this number?
Yeah, sure. There's two more. Can you explain the debate structure a bit more again?
Yeah, sure. So when we do this debate re-ranking, what we do is we pass in the abstract of the original paper. In this case, it's just this query, but in our test set, it was the abstract of the query paper. So we pass in the abstract of the query paper and then the abstract of all these papers that have been retrieved. And then we ask the LLM, okay, why should I include this paper in my review? And then we also ask it to generate arguments for why I shouldn't include this paper in my literature review. And based on these arguments, we then ask it to give one final score, which should be proportional to the probability of this candidate being included in the final lit review. So, and at the end, we just sort based on this relevance score. And what's cool about this is when it generates these arguments, it knows what other papers are in the mix as well. So it learns to it better situates its arguments in this setting.
Okay. And there's another question which just says that would a reasoning LLM fare better?
Yeah, of course. So this one is, I guess, for this demo, we are using GPT-4. In our experiments, we used Llama 3.1 and GPT-4, but it works with any LLM. And if you have a reasoning LLM, I would guess it would lead to better results for sure.
Okay, great. And I got another question in this personal chat, which says, how do we confirm that the check mark, which is being used to prevent hallucination, is actually working? And does it affect the system's speed or efficiency? Also, how is this approach different from something like Notebook LM, besides the fact that I'm not manually adding my own sources? And is there a specific database the system was trained on?
So I'll start with the last one. We are not training anything here. Everything is like on the fly, except the that specter embedding thing. But what was the first question? Sorry, again. How does it fare
So,
against like Notebook LM? Okay, so in Notebook LM, yeah, you first have to provide all these papers by yourself. In this one, we do the like both the jobs. We given your idea, like we first retrieve what the like, relevant things should be, and once you have these things, you have all this control over uh, how you want to structure your review at the very end. And one other thing I observed with Notebook LM is it's kind of, I don't know, maybe I just haven't prompted it enough. It always seems to think in like bullet points, right? um, that was I guess at least my experience. You can correct me if I'm wrong.
and there's a follow-up question from Nishan. He's asking that in this case, don't you think using a different model or a family of models would be better because there was a ranking of how models look at itself and the others and how that's slightly different?
Yeah, so when we did these experiments in the paper, we did not have these models. So we relied on what the latest and greatest at that time was. But of course, yeah, you can plug in any latest LLM into this system and it's gonna potentially work better. And I mean, so even with something very small like GPT-4 or Mini, we already see, like at least in my experience, I see very like relevant literature here retrieved, because the job of the LLM in this case is not very, like, it's not doing a lot of the heavy lifting, right? So the like major job that is it has to do is this re-ranking job, and for this apparently even smaller models are good enough. Maybe for writing the review, if we switch to a bigger model, they are gonna follow your instructions better, and maybe they're gonna come up with a better plan. So yeah, for the second step, if you include the most recent LLMs, it's gonna
Great. And one more thing that we missed from the question was that this whole hallucination avoiding step, does it cause any, like, does it affect the system's speed or efficiency? And also, which component is the one taking most time in this whole pipeline? Um, am I audible? Is it my internet or Gaurav's? Can someone in the chat confirm if I'm audible? Okay, I think it's Gaurav's internet. Okay, great.
Yes,
Yeah, Gaurav.
but
Okay, great. Yeah. So yeah, there was one last question that we missed from the chat that which component is taking the most amount of time in the whole pipeline? Gaurav, you're on mute. Sorry. Okay, just
so
a
yeah, I
minute.
would say it's the search step, and if I want to be more specific, it's going to be the re-ranking module, the LLM-based re-ranking module, because that step depends on, the speed of that step depends on how many papers are we passing to it at once.
Mm, yeah, makes sense. Okay, great. Yeah, so these were all the questions from my end, and it seems like we have converged to solutions. And oh, another question. How expensive is the inference cost?
That's a good question. We have a table for that in the paper as well. Let me pull. So I'm actually looking at the paper for some of these questions. Um, let me. Oh, by the way, someone asked about the normalized recoil as well, right? So there's a worked out example in the paper in the appendices, if you are interested. Um, Comparative analysis. Okay, yeah, this one.
Like me to share the paper, like the screen of the paper.
Yeah, I'm sharing the screen. Okay, so this is how much it costed us for these experiments. So with LLMs, it's sorry, with open source models, it's like zero. But if you want to use GPT-4 with permutation re-ranking, it's 50. However, like we are uh, with all these things like Olama and stuff, you can run an LLM on your local machine and then attach, like plug this whole system to your locally running LLM, and then the monetary cost at least will be like zero. And yeah,
Mm, makes sense. Right. Okay. So I guess that was quite a productive discussion. Thank you so much again, Gaurav, for the talk. And if anyone from the audience has more talks, I think you're reachable on LinkedIn and Twitter.
yeah, of course.
Okay, great. Thanks again for the talk, and thank you for the audience for showing up. We'll meet again in next few weeks for another session. Thank you so much, Gaurav. Best of luck.
Thanks for having me.
Bye bye.
Bye.